G for kinetic energy. So now what we're going to do is go to outer space where there's no friction and there's just going to be one force that we apply to a mass, and then it will accelerate. And then we will let it go, and it will be traveling with some velocity v. So say here at the beginning, say it's at rest, we apply a force for a certain distance, d, which I'm going to go ahead and call x, and then we let go. We're going to derive a formula 3 ways. Here's method 1. Method 1. So we take the work is force times x for this problem. And since we have a net force, we're going to have acceleration. In other words, F is going to equal to ma. And since the force is constant, the acceleration will be constant. Now, if the acceleration is constant, then it will be equal to the change in velocity over the time. And since it starts out at rest, it's just going to be v over t. And the distance traveled, you can get the distance traveled by this cool formula. These are 2 kinematic formulas we saw earlier. The average velocity times t, but since we're starting from rest, this is simply vt over 2. So what we're going to do here is write this as ma x, put the a in for the a, and put the x in here. And when we do that, we will get m times v over t times vt over 2, and that's, the t's cancel, that's 1/2 mv squared. Now that's a natural occurrence, or say evolving of a new physical quantity, and it has the same dimensions as work. But this is in the moving body, so we say that the work that you did has been transferred into the moving body. There's energy now, and that's called the kinetic energy. Don't know why I said kinetic twice there. Let's fix that. If I were teaching in class, someone would have caught that, but since this is a video, it takes me a while to catch some of my mistakes. Okay, so that's derivation 1, and this is called K, kinetic energy, 1/2 mv squared. That's derivation method 1. So now we do method 2, and method 2 is the method I really like for this course. For method 2, we're going to start with some initial v0, and then apply the force, and then at the end, look at the velocity v. So the only thing difference in this case, when we have F is ma and x, the acceleration now is going to be v minus v0, where v0 is not 0, over t. And then here, the x is going to be 1/2 v0 plus v times t. And when we do this, we'll have for the work m, this will be v minus v0 over t, and then we'll have a 1/2 v, I'll put the v first, plus v0 times t. The t's are going to cancel, and guess what happens when you have the sum and difference of 2 terms? Okay, well, this will be 1/2 m, put the 1/2 out front, m, and this is v, we'll put down v plus v0 and v minus v0. That's going to be v squared minus v0 squared. So in other words, we're going to have 1/2 mv squared minus 1/2 mv naught squared. So this is the initial kinetic energy here, and this is the final kinetic energy. Some books would like to call that, say, initial, and say this final. But the point is, it's a change in kinetic energy. So the work that you do is equal to the change in kinetic energy. And this is when you have a net force, so you have acceleration, a net constant force. See, kinetic energy arises naturally in that second method. And here the third method is one that uses calculus. And if you haven't gotten this far in your calculus 2, that's okay. You can skip it and come back later. But the benefit of this method is that the force can be a function of position. In other words, force can change as you pull along. So in that case, we're doing an integral, force dx, and we're going to go from here, say, x naught to x. If you don't like that x up there and the x here, you can make this a capital A. Pick a specific x, and it works. Because when I first studied this, it kind of made me a little nervous when we would use x twice. So you could let this be a fixed A. All right, then if we do that, we would get here x naught to x, like that. We would have m, a, and here ma. I'm going to write that as m dv dt. That's the acceleration, the change in velocity at respective time. And now we're going to use a little calculus manipulation. We're going to write this out here where this is a dv dt, and then we'll have a dx dt, a chain rule kind of thing in calculus. And this is v. So this is, here when you do that, you should change this to a t naught to t, because that's the integration variable. And I'm going to now go to a velocity integration variable, because I'm going to have here, this is, well, we're going to do it in a couple steps if you want. Here, this is a dv dt times v dt. And then I'm going to do this as mv dv. All right. So then we go here. This is going to be an m, a v, and a dv. And if we integrate this, we get v squared over 2 from v naught to v. And we get the same results we did before, 1/2 mv squared minus 1/2 mv naught squared. Isn't that nice? So there's 3 derivations here, or 3 methods to arrive at this kinetic energy, and that the work is equal to the change in the kinetic energy.